We're going to give two examples of entropy compensation principle. The first one is engines. An engine is a device that goes through a cyclic process. So we show the engine with this circle. So this M is the engine. Because it's a cyclic process, the entropy change is zero, internal energy change is zero. And this is going to convert the internal energy of a system into work. So the purpose of the engine is to convert internal energy of a system to work. So work is the useful output that we obtain from the engine, and in doing so we have a cyclic process. And because entropy and internal energy are state variables, delta S in the process is zero, and the change in the internal energy of the engine is zero. So it's converting internal energy of a system to work. But it's not the internal energy, there's no internal energy change in the engine itself. So it consists of a heat reservoir. So here we have a heat reservoir that's basically fixing the temperature at T. And from this heat reservoir, we basically absorb some heat to the engine, and the engine goes through a cyclic process and produces an output. Now, for this engine to be a perfect engine, we must have the work output of the engine equal to the amount of heat that we're absorbing from the reservoir. So that would be the ideal situation. So if you have an ideal perfect engine, would have the amount of heat that is absorbed from the reservoir, heat Q absorbed from the reservoir A, must be equal to the work output W. So if Q is equal to W, we have a perfect engine. Now, if you think about the second law of thermodynamics, so is this possible? So if I look at the entropy change in the reservoir, so I have the entropy change delta S in the reservoir A. It's providing heat Q, therefore heat is extracted, the heat added is negative, so minus Q at constant temperature T. So that's the entropy change in the heat reservoir. And the entropy change in the engine, delta Sm, is equal to 0. Why? Because it's a cyclic process. The entropy is a state variable. And therefore, if you write the entropy change in the total system, so if I call this system, let's be consistent with our previous discussions. So let's call this system A star. So delta S, the total entropy change, delta S star would be equal to the entropy change in the heat engine plus the entropy change in the entropy change in the reservoir plus the entropy change in the heat engine, and that would be equal to minus Q over T plus 0, so it is minus Q over T. And basically, according to the second law of thermodynamics, delta S star must be greater or equal to 0. This is second law of thermodynamics. however, I found that if you build a perfect engine, the entropy change in the total system, isolated system A star, would be minus Q over T. Therefore, we find that a perfect engine cannot be built. And because it violates the second law of thermodynamics. However, we want to get a useful work output from such a device, and therefore we can use our principle, the principle of entropy compensation. And the principle of entropy compensation says you need an auxiliary system that is going to make sure that the total entropy change is going to be equal to or greater than 0. So now I'm going to have another heat reservoir. So basically I'm going to call this now hot reservoir. So this is my hot heat reservoir. And then here I have the cold reservoir. And the isolated system here is actually not this one. The total system, total isolated system would be the hot reservoir, the engine, and the cold reservoir. So that would be the total isolated system. So this would be my new A star, the new total isolated system. So if I do this, let's see the consequences of doing that in the entropy. So I'm using the principle of entropy compensation, where A prime, the cold reservoir, is the auxiliary system. So what happens in this case? I look at the way the heat flows. I have heat being absorbed from the hot reservoir and heat being released to the cold reservoir. So that's Q prime. And the cold reservoir is at temperature T prime. And by using energy conservation, since delta E bar in the engine must be equal to 0, the heat provided to the engine, delta E bar, the total heat provided to the engine is heat absorbed Q and heat released Q prime, Q minus Q prime, and the work done on the engine is minus W because the engine is doing work. This must be equal to 0. So the work output is going to be equal to Q minus Q prime. So this is heat absorbed Q, and this is work done on the engine W. So that's basically the first law of thermodynamics. So I have used the first law. Okay. Now, if I look at the second law of thermodynamics, I look at the entropy change in system A, delta SA, which is the reservoir. It's providing heat, so heat is extracted from the system at temperature T, minus Q over T. The entropy change in the engine must be equal to 0 because it's a cyclic process. The entropy change in the A prime system, which is the cold reservoir, the auxiliary system, that is heat being added to the system, Q prime, at a constant temperature, T prime. So you can see that we're absorbing heat at a constant temperature, T prime. So if I look at the total entropy change, it is minus q over t plus 0 plus q prime over t prime. So it is q prime over t prime minus q over t. So basically this has to be greater or equal to 0 for the engine to be realistic. So I'm looking for a realistic engine here, and in order to have the compatibility with the second law of thermodynamics, the total entropy change, delta S star, must be greater or equal to 0, second law. And so if I write q prime over t prime minus q over t should be greater or equal to 0. And if I substitute for q prime, q minus w, I see that this is basically q minus w over t prime minus q over t should be greater or equal to 0. In other words, in q parentheses, 1 over t prime minus 1 over t should be greater or equal to w divided by t prime, or I can write this as the work output of the engine divided by the amount of heat absorbed from the hot reservoir should be less or equal to 1 minus t prime over t. So T prime is the temperature in the cold reservoir. So let me make sure that this is the cold reservoir temperature and this is the hot reservoir temperature. 1 minus T prime over T. So we find that there is a theoretical limit on this ratio, W over Q should be less or equal to 1 minus T prime over T. So in order to have a maximum work output, so to maximize W, this gives us a remedy which says T must be as high as possible and T prime must be as low as possible. So with this we're going to have the maximum possible or we will be basically maximizing the work output. We define this ratio eta W over Q, the useful output of the engine work divided by the amount of heat we have to absorb, which is also equal to Q minus Q prime over Q. This is called the efficiency of the engine. Efficiency. And as you can see, the efficiency of the engine has a maximum value which is T minus T prime over T. This is the theoretical upper limit on the efficiency of the engine. Theoretical upper limit. And if you have the theoretical upper limit, if eta is equal to T minus T prime over T, this is going to imply that delta S star is going to be equal to minus Q over T plus Q minus W over T prime, which is Q times 1 over T prime minus 1 over T minus the efficiency, and that will be equal to Q times T minus T prime over T prime minus T minus T prime over T prime, which is 0. So delta S star must be equal to 0, and this is going to be true if it's a quasi-static process. So the process that we perform on the total system A star, basically it says the theoretical limit can be obtained is only reached if the process that we perform in the system A star is quasi-static. And remember, for a quasi-static adiabatic process, we're going to have delta S star as the integral dq over t. This must be equal to 0. So this is only possible if it's a quasi-static adiabatic process that we're performing on the overall system. The overall system, A star, is not exchanging heat with its environment, so it's already adiabatic, and therefore the process also has to be quasi-static so that we have no entropy change. So this conclusion that we have this upper limit on the efficiency of an engine is recognized by Carnot's theorem. So Carnot's theorem states no heat engine operating between two reservoirs at temperatures T and T prime can be more efficient than a quasi-static engine operating between the same set of reservoirs. So this statement, which sets the upper limit on the efficiency of a heat engine, is known as a Carnot theorem. Okay, so in order to give an example for the principle of entropy compensation, we worked on one of the basic features of industrial revolution, that is to build an engine that provides a useful work in a cyclic process. And as you can see here, if you have only a hot reservoir at temperature T that's providing heat to an engine that operates in a cycle to produce a work output, and since you have a cyclic process, there is no entropy change in the engine, and there is no mean energy change in the engine because we have the same initial and final states. So the heat engine absorbs amount of heat Q, work output W. They should be the same in the ideal engine, but since the entropy change in the hot reservoir is minus Q over T, entropy change in the engine is 0 because it's cyclic, total entropy change would be negative, which violates the second law of thermodynamics. So a perfect engine cannot be built. If we use the principle of entropy compensation to introduce an auxiliary system, A prime, that's the cold reservoir at temperature T prime, which also absorbs an amount of heat Q prime from the engine, we see that using the energy conservation, because we have no energy change in the internal energy change in the engine, W must be equal to Q minus Q prime. The entropy change in the hot reservoir is again minus Q over T. In the cold reservoir is plus Q prime over T prime. The total entropy change, Q prime over T prime minus Q over T, must be greater or equal to 0, boils down to the condition the work output divided by the amount of heat absorbed from the hot reservoir is less or equal to 1 minus T prime over T. So the temperature T of the hot reservoir must be as high as possible, T prime must be as low as possible in order to have the maximum work output from such an engine when designing an engine. So this ratio, the useful output work divided by the amount of heat that we have to absorb from the hot reservoir, is called the efficiency, and the efficiency has this upper limit, T minus T prime over T, where T is again the hot temperature reservoir, T prime is the cold temperature reservoir. And this implies that the delta S star, the total entropy change, will be equal to 0, and as you know, the total system is isolated and it doesn't have heat exchange with its environment, so the process that is performed on the total system you can call adiabatic, but this says that it also should be quasi-static because the entropy change is going to be 0. So Carnot's theorem states that no heat engine operating between two reservoirs at temperatures T and T prime can be more efficient than a quasi-static engine operating between the same set of reservoirs, which makes sure that the entropy change of the total isolated system is going to be equal to 0.